Go ahead and start recording this. We averaged 66. That ain't bad. I like an average to be the 68 is my target for class. That's how. Say anybody writes an exam that everybody makes a 90 and above on is a sucky exam, because not everybody knows the material that well. And what I have to do is figure out who does and who doesn't. So you can not make over a 70 on an exam. You're still going to be in my class. It requires that you do fairly well on the clickers, that you do well in your mastering chemistry, and you do your labs. Okay, so that's the way the class is weighed. The thing I'll tell you today is figure out what you missed. Why you missed a question. Several students last semester, when we took Gen Chem 1 last semester, I had 6 students that we had 26 in that class. 6 students out of the 26, the final exam was their highest exam of the year. Okay, that's what you want. You want to put it together all at the end, figure things out. So, I'd say that based on my grading scale, there was only one person that failed the exam. So I think that's pretty good. If it were 2 points higher, I'd say it's spectacular. But there were a couple questions on there that maybe challenged you a little bit, and we're going to go over the test. So here's just some information. I've shared this with my students that had me in first semester. This is a plot of your mastering chemistry versus your exam score. So I took the average of the 3 assignments. I didn't do the math primer or the intro, but the 3 assignments that we have from this chapter versus your mastering chemistry score. And there's, in general, a positive trend that goes up. So for the most part, if you didn't do much on your mastering chemistry, you didn't do much on the exam. And students that tended to do well, now I would love to say that everybody fit in this group. And the reality is, I know it doesn't. So these people that invested the time to do excellent on the mastering chemistry all got A's on the exam. The reality is that some of you still did fairly well on the mastering chemistry, but you may not have got the exam score that you hope for. The key thing I'd tell you when you look at this, start looking at to change your study. Do you need to focus more on the multiple choice type questions? Do you need to focus on the free-form type questions? What was the thing that you could do to improve the most? Okay, and that's how you want to change for the next exam. Everybody studies differently, and there were a variety. Some of you did very well on the ones on the back. Some of you did very well on the ones on the front. And there's a couple that did well on both. So you got to figure out where you are. Okay, if you have a question about anything, so the Scantrons show your correct score. I encourage you to keep these to study hard for the final exam. Certainly keep all your graded material just to make sure that I didn't put something in mastering chemistry wrong. You may have made a 97 and my dyslexia put it in as a 79. Okay? That's the way that you prove to me if I misentered the score is you show me the paper. I encourage you to look at your score and make sure that that it's calculated correctly. So just so you understand how our scores are calculated, there were 25 multiple choice questions that were worth 3 points apiece. There were 36 points out of the 6 on the back. So if you add that together, that's so many out of 111. And what I do is choose to round up. So whatever your number is, added up on those total number of points from the front and the free form on the back. And then whatever your score is that's put in here. All right. So circled is what your grade is. And that's the way that I grade. And I choose to, the way I do it is I don't put a fractional or decimal place in. If you're a 0.1, if you're a 0.05, I round up. Okay, so you get the extra point. That's just the way that I do it. Okay, so just going to quickly go over some of the questions. And I've highlighted some ones that were problem questions. And when I say that, to me, a problem question is 50% of the class missed it. And there were only 3 questions on the exam. Three questions on the exam where 50% of us missed it. So we did really good on the multiple choice as a whole. All right. If you have a question on any particular one, ask it. Okay. I'm going to go through these. Just go through these first pages. Let's see. I think maybe we did well on 9. We did well on 10. This was like a problem from last year, but it said strongest. I changed it to weakest, so you're looking at the thing with the lowest enthalpy of vaporization. Did very well on 11. Good on 12. We did good on 13. 14, 15 was the first one that we stumbled on as a class. It says, which one of the following should have the largest Henry's Law constant in the water? So Henry's Law constant tells us how much gas is dissolved at a certain pressure of the gas over the solution. So what happens is things that are more soluble have a larger Henry's Law constant. Things that are going to be more soluble is like interacts with like. Light dissolves light. You're looking for something that I tell you it's water in the problem. So you're looking at things that has similar characteristics to water. What do we know about water? Water can hydrogen bond, and water is polar. And so the fact that it's polar means it's unsymmetric and that it has a dipole moment. So possibly it could do dipole interactions. And if I look at these different compounds to try to figure out which one's going to be most like water, that's what I'm trying to figure out. The ones most water-like, polarity is the thing that I'm trying to answer. Are any of these compounds polar? So first one I look at anything that's monatomic is nonpolar. Okay? Because there's no distribution of electrons, so that's nonpolar. Diatomics are going to be nonpolar. If I look at this is ethane, it's nothing but carbon-carbon and CH bonds. That's going to be nonpolar. But if I look at carbon monoxide, so carbon has a electronegativity of 2.5, oxygen's 3.5. That means there's a difference in electronegativity. This means that it's going to have a dipole associated with it. A dipole means that it can have a polar interaction. So the one that's going to be most soluble and have the largest Henry Law's constant is C. That's a critical thinking problem. Okay, and I probably threw a few more critical thinking problems in these. All right, and when I grade these, I pull the sheets and I flip them over. I don't know anybody's names, and I grade one problem at a time. I do everybody's problem number 26 and everybody's 27, etc. 2 of you had issues but I remember it because you repeated the problem. You had your units reversed on molar mass, and that's something you absolutely need to correct. Okay, so if you're one of those 2 people, you need to make sure that you correct this for the future. When you look at molar mass, it tells you the number of grams per mole, and you had those inverted, and you inverted them, I think, in all of your calculations. You just make sure in the future you correct that if you're that person. The key now tell you, if you do your problem with dimensional analysis, your units will always cancel out in a way that the unit that you're looking for is the one that you're left with. So like in this particular problem, I want to know how much of a substance we need. So an amount is the volume times the concentration is going to give me the number of moles, and then I'm going to take moles and convert it into mass with the molar mass. So I take the concentration times the volume, and I took the milliliters to liters, so now liters would cancel out. And then I multiply by the molar mass. That lets the moles cancel out, and I'm left with grams. Okay, that's the thing that told me that I did the problem right. Is I've got the unit that I'm looking for left on top. And we'll see on one of the problems on the back page, a lot of you had an inverse of something. If you looked at your units And when you followed your dimensional analysis, you would have had inverse liters instead of adding liters. I know it seems maybe too trivial to set up those units and do dimensional analysis, but it's worth your time to do it, I promise you. We did good on 12 and 13. I went backwards. Sorry. We did good on this one, so 18 through 20. We did pretty good on. 24 and 25 slaughtered us. Okay. So 24 was choose the solute with the lowest Van Hoff factor, so that's the I. And I gave you a group of compounds. B, C, and D all had something in common. What was it? They're nonmetals and metals. They're ionic compounds. That means they dissociate into multiple particles. Okay, so this one, the I is going to be 2. This one, the I is going to be 4. This one, the I is going to be 3. What made this one's different is it's a molecular compound. And with the molecular compounds, I is equal to 1. That's what you need to recognize. That's a critical thinking thing. Okay, so it was something out of the box. I don't think I've asked a question like this. Do you really understand this topic? Okay, all right. The number 25, we did a problem kind of like 25, or very similar to 25 as a clicker question. It says choose the compound with the lowest vapor pressure. So you need to look at the one with the lowest vapor pressure and figure out which one that's going to be. And I tell you to assume the Van Hoff factors are ideal. So I gave you these different compounds, and we wanted to get the one with the lowest vapor pressure. Means we want the one with the greatest number of solute particles in solution. The more solutes there, the less solvents on the surface to go into the vapor phase. Okay? So if I look at this first compound, it's a molecular compound. This is acetone. I is 1. So that means the effective concentration is just the same as the molality. Then if I look at this one, this is the carbonate polyatomic ion, CO3 minus 2. This is going to form the lithium 1 plus. This is going to have an I of 3, so 3 times the concentration, it's going to be 0.18. Okay, on this guy, this is the ammonium, Na4 plus, or NH4 plus. The sulfate forms a 2 minus. So there's 2 of these and 1 polyatomic ion, it's going to be 3. So times the 0.04 is 0.12. And then the last one, it has an I of 2. If you remember, this polyatomic ion is called acetate. So rubidium acetate, 2 times is 0.6. We want the one that's got the most. So that's the reason it's choice C. It's thinking through it. Okay. A little bit more maybe challenging in those aspects than maybe what the previous exams were, but certainly in line with some of the things that you did in the Mastering Chemistry. Okay, so we'll go over quickly these ones at the end. So how much energy is gained or lost when you've got a certain mass of dichloromethane? That the key is that it condenses. Tell you it condenses at its boiling point, and I give you the enthalpy of vaporization. Okay, so we're looking at condensing, so we're wanting to go from the gas phase into the liquid. The first thing to think about is that an endothermic process or exothermic? Is that getting heat, absorbing heat, or losing heat off? Losing heat off. So this is an exothermic process. That means that Q is negative. Okay, so it's losing energy off, and the sign's going to be negative with this. And the way that you can think of it is that condensation is the equal and opposite of the vaporization. So you just change the sign. So Q is equal to the number of moles times the enthalpy. So I need to go from grams to number of moles by dividing by the molar mass. The grams methylene chloride or dichloromethane cancel out, and then multiply by the enthalpy. Grams are the moles of dichloromethane cancel out. The sign is negative if you follow the equation above, and you get a negative around 5.5 kilojoules. If you use the word lost, I gave you credit. Otherwise, you had to have the sign. Okay? Because that's what, this is part of the question. How much energy is gained or lost? Is it going in or going out? Because it makes all the difference in the world. Yes?
If you, like I forgot the negative, so did you count off? I put that it was lost, but I didn't.
If you got 6 points, I gave you all of it. Now, if you wrote the word lost and I took points off, I missed it. So I will correct that. So, and certainly if there's something, if there's a math error that I made, I'll correct this, no problem. Just immediately after class. Always don't have a problem questioning my grading. If you have a question with something, I encourage you to come talk to me about it. Let me explain why I did what I did. Okay, so other questions on this one? All right, let's look at the next one. All right, I'm gonna shut the door. I talk so loud. I want to tell them answers. They're only across the hall. Okay, bet every one of us negative on that. All right, so 27 says you've got a compound and it gives me some vapor pressures, it gives me some temperatures, and I want to determine the enthalpy of vaporization. So I know a P1T1, a P2T2, this is the 2-point Clausius-Clapeyron equation. Most of you recognize the equation to use. You put everything in. You knew to put the temperatures in Kelvin instead of Celsius, so you made that conversion. If you were here and that's all you got half of the points. All right, but then to solve it, if you take this ratio, takes the natural log of it, you get 1.83. If you take the inverse of those temperatures and subtract it, you get a negative 6.08 times 10 to the minus fourth. And then we know the value of R. So if you just do the math to rearrange that, you get 2.5 times 10 to the fourth. And if I move the decimal place over, it's going to be 25 kilojoules per mole. Some of you just got lost in the math. And some of you had problems with your calculators. You and your calculator don't like each other. Because you wrote absolutely everything down right. But if that's the case where if you had a math error, you maybe got a couple points if you rearranged something wrong. Some of you, when you cross multiplied over, you left something on the top. It should be on the bottom. That cost you 2 points. If you wrote everything down right, so if you got to right here and you didn't get this out of the end of it, I either put math error or calculator broke. Yeah, that's my sarcasm saying that you don't know how to run your calculator. And you've only lost a point on that. Okay, because you were there, you just couldn't get your calculator to give you the answer out of it. But that's what the coding means. All right. Questions on that one? Okay. Let's look at 28. So ethanol, I'll give you the temperature it melts at, 114 negative degrees. I give you the enthalpy of fusion. So that's the energy required to convert it from a solid to a liquid. I give you the specific heats for both the solid and the liquid phases. And I want to know how much heat is needed to convert 25 grams of solid that's starting at a minus 125 into a liquid at a minus 80. So you have to think about what's the heating curve that's going to happen. You're starting as a solid at minus 125. The first thing you have to do is heat the solid to get to the melting point. So this is going to be the Q1. All right. So in Q1, that's going to be the heating curve that's happening as you heat the solid to the melting point. Then you have to melt the solid. So that's going to be our Q2 for us, is the energy required to melt the solid. And then the final transition is to go from the liquid now to the liquid that's at minus 14 or minus 114 up to minus 80. So this is going to be Q3. This is to heat the liquid. So it's mass times specific heat times change in temperature. All right. The mass is 25 for the liquid, or for the solid. The specific heat is 0.97. Bless you. Final temperature is 114. Initial temperature is minus 25. It comes out to 267 joules. If you convert it to kilojoules, it's 0.267. The next is the fusion. It's the number of moles times the enthalpy of fusion. Find the number of moles. You take the mass, divide it by the molar mass. Grams cancel out. That gives you moles times the enthalpy of fusion. Moles cancel out. That one is 2.7 kilojoules. And finally, the last step to heat the liquid, 25 grams, the specific heat. The final temperature is minus 80. The initial temperature was a minus 114. Minus and minus make it a positive, so the temperature is going up here. So you multiply that one out, you get 1955 or 1.95 kilojoules. You add all those together, it's a little bit less than 5 kilojoules that have to be absorbed. All right. To get close to full points, you had to show the 3 independent steps. Some of you went from here to here in one heating step. And then you added enthalpy to it. You've got to break it into the different regions. Because there's a different specific heat associated with the solid than there is with the liquid. So based on how far you were or how close, that's how many points you got on that. Okay. Question on 28. All right. We did several problems like that guy. And there were examples off the old test. 29 says you had some KCl that's made by dissolving a certain mass of KCl in a certain volume of water, or a certain mass of water. And I wanted to know what the vapor pressure was of the solution, which is the water is the solvent, given the vapor pressure of pure water at that temperature was this. All right, so we were given the vapor pressure of the pure solvent. To do this, the vapor pressure of the water in the solution is equal to the vapor pressure of the solvent times the mole fraction for the solvent, which is water. So what you need to do is find out how much moles of solute, KCl, was there, how much moles of water was there. So if you take the KCl, the mass divided by the molar mass, it's 0.335 moles. If you do it for the water, it's the 250 grams divided by 18.02, 13.87 moles. Then I find the mole fraction for the water. It's the moles of water divided by the moles total. It's 0.9764. And then finally, you apply it to Roloff's law, the mole fraction of the solvent times the vapor pressure of the pure solvent. You get 23.2. Okay. We varied on that one. Some of you tried to solve it with the Clausius-Clapeyron equation. Some of you gave me kilojoules of energy for an answer, and you were just on the wrong track. We were looking for something that was a pressure. 30. I tell you on 30, this is a type of problem you're going to have to do in every other chemistry class you ever take. You're going to have to give a volume of solution and know how much volume you need to get a mass, or a mass to get a volume. In this case, I want to know what is the volume. I give you a concentration in the form of molarity, and I know how much of the solute that I want. I want a certain mass of it. You start with what you know. So I know that amount is equal to concentration times volume. So that means volume is going to be equal to the amount divided by the concentration. Just rearrange that. So I'm starting with that piece of information. So I'm going to take the amount that I want. I want the 30.5 grams of KBr, and I'm going to divide it by the concentration, which is the 0.716 moles per liter. Okay, so when I think about what's going on, I need to take grams of KBr to moles. So I divide by the molar mass. Grams of KBr would cancel out top and bottom. That leaves me moles of KBr. That lets moles of KBr here and here cancel out. So now what I've got is this units of liters are on the bottom. So if it's on the bottom of the fraction, it would go to the top. All I need to do, you could have left it in liters. If you left it in liters and got 0.358 liters, that was a correct answer. I chose to take it to milliliters and get 358 milliliters. That was fine. I didn't say what unit I wanted the liters in, but a lot of you got whatever the inverse is. It's like 2.5. But if you looked at your units, you took and you had this term, you had everything inverted. You had the whole problem inverted. But if you looked at your liters when you did this, you had inverse liters, if you really tracked your liters out. So you needed the inverse of that to do that. I mean, dimensional analysis tells you if you're doing it right. That's I just can't emphasize that enough. All right, last one. Tricky problem. Okay, so this is the, I tried to give you a hint. I tell you it's an aqueous solution. We talked about what aqueous solutions were in the start of chapter 13. That means it's a water-based solvent. That's the definition of what aqueous is. So I tell you, an aqueous solution has a normal boiling point of 103, and I want to know what is its freezing point. And I give you the case of B and case of F for water. And then as the hint, I gave you what is the same for these two solutions. The thing that's the same is we know something about how much the boiling point has changed. Right? So I told you it boils at 103. So the difference in the boiling point is that of the solution less that of the pure solvent. We know water boils at 100. So the difference was 3. What's the same about this is I know this term, I know the case of E's given, is the molalities are the same between the two solutions. So use the given piece of information in the first sentence to solve for molality. So the 3 degrees divided by the boiling point elevation constant tells me the molality is around 5.88 molar of the solute. Then I can apply that to the second part of the problem, to the freezing point depression. Now I know what this is. I'm given the case of F term, the freezing point depression constant, and it comes up to 10.9. And the fact that it's a depression, I know it's negative. So this solution is going to freeze at 10.9 degrees. That's putting the pieces of the problem together. Okay, that's maybe a tricky, but it's certainly doable based on the things that we talked about. Okay, good news is exam 1 is done. Bad news is you may not have made the score on exam 1 you wanted. There's always redemption because there's another test coming up soon. I hope you like math because there's fixing to be more. Chapter 14's topic is kinetics. Okay. And we'll let y'all get your notes out. I'm going to check out my test tape real quick. So I need my flippers here. All right. So the topic associated with chapter 14 is kinetics. You'll do kinetics. For those of you that take biochemistry, if you're a pre-professional and you have to take biochemistry as part of your degree plan, you'll do a lot of kinetics in biochemistry. Determine rate constants for enzymes. It's critical to understand biological processes and how enzymes work in systems. This is kind of our introduction to kinetics. So we're going to talk about the rates of reactions and how we define those, how we calculate the average versus the instantaneous, and then we're going to go over some of the rate laws, what the rate constant means in rate order, and we're going to talk about in particular 3 types of reactions: the zero order, first order, and second order. Okay, there are orders other than these. This is just the introduction to it. So you may take another class where you end up with a fourth order reaction. That's possible. It's just some different equations that's used. And then we talk about only things that are whole orders. In reality, we found out that there are reactions that may be 0.5. It's not always integer. So we're taking a simplified view of it, but I want you to understand it's not always as simple. How we determine the order, so y'all are going to love that part. And then what happens with multiple reactants. Then how we can apply the rate law into something called the integrated rate law. And what it allows us to do is determine the concentration as a function of time. I start off with a certain concentration of reactants. What is the concentration of products after 10 seconds? After 1 minute? After 1 hour? Okay? That's what this is going to allow us to do. In the world of engineering, how long do you need to let a reaction run before you stop it? It's critical you understand that. Some reactions occur almost instantaneous. Others are very, very slow to happen. Okay? We got to know something about them. And how do we treat the different orders? All right? Then we're going to talk about a term called half-life. It'll apply, again, this concept of half-life when we talk about radioactivity at the end of the semester. How long does it take to get halfway there? And then we're going to talk about, get into, since y'all are going to love math so much, get into the effects of temperature and the radiance equation, and we'll do a lot more logs. How to look at the radiance equation, calculate activation energy, and then how we can calculate what a new rate constant will be at a new temperature given some conditions from a single system. And then finally, we're going to talk about the influence of catalysts and a couple of different types of catalysts, homogeneous versus heterogeneous, and then how enzymes play a role in biological systems. Critically important. Almost every chemical reaction that occurs in the body is aided with the function of an enzyme. So we have to understand how they work. In the body, in living organisms, reactions happen amazingly fast. And the why because of that is these molecular machines, enzymes, aid those chemical reactions, allow them to do it. Again, I strongly encourage you to look at the set of problems. I would encourage you to go back and look at the calculations or the problems at the end of the chapters from the previous 2 chapters versus the problems that I put on the test, and look at the similarities. Okay, because some of them were modeled right off those problems. Not all of them, but some of them came from those types of systems or those types of problems. Okay, and the thing I'll tell you is, you know what you made on this test. What do I have to do to improve? The thing I'm going to ask you, did you work all the problems? Did you individually do all the mastering chemistries? Or did you get a lot of help on doing them? Right? Did you read the chapter? Those are the things I'll ask you to do. Did you watch those videos that were on the e-textbook? Because those are some pretty fruitful little videos. Those little 2 and 3 minute videos the author puts through there. I mean, things that you can do to get where you want to be. I mean, I understand not everybody's striving to get an A in this course. I want you to be able to get what you want. Okay, so if you're, all I need's a D and I slide out of here and I can go get my next degree, okay, right? But if you're wanting to get in a professional program where if you're wanting to go to med school, average GPA to get in med school is a 3.85 at OU this year. All right, 3.85. You can't handle many C's and D's on your transcript to maintain a 3.85. And that's just the reality of it. I want you to be realistic with what you want to accomplish. Okay, so lizards. All right, so ectotherms. So we're going to think about biology a little bit. They're examples of cold-blooded creatures, along with snakes, whose body temperature will match the environment. So we were out on the water this weekend, or near the water. I live out at Lake Durant, and there was a fairly large water snake that swam up to us while we were cleaning some brush and stuff. And I always thought this year snakes were hibernating. Obviously, this one's not. So he wasn't moving terribly fast, but his length was big enough. He was at least 6 foot. Made me evacuate the premises, and he got to have the brush. So, but these are animals whose body temperature matches the environment. So when it's cold, their body temperature changes. Now, us, what happens if our body temperature drops below about 94? We're in hypothermia. We're in shutdown mode. Okay, so healthy body temperature is what in Fahrenheit? Okay, so 98.7, 98.6. What is it in Celsius? 37 Celsius. So that's our, and it's a couple of degree window. If you're not in that window, you're sick. When I had the flu last week, when you're young, you get fevers and you can handle it. So my 15-year-old had the flu first. I think that's who gave it to me, and I was the one that I took him to the doctor, and I was the one giving him his meds and putting moisturizer on his head. I mean, he slept through 103.5 fever for a couple of days straight. My fever got to 102, and I thought I was dying. I mean, I kept looking at the thermometer going, this thing's wrong. It's got to be 108. I mean, I thought it was a lot higher. When you're young, you can handle temperatures a lot better than when you're older. Your body adapts. I haven't had a fever like that in a while, but I could swore it was a lot higher than it was. So there's some very funny videos of some wife has put up her husband that's got a cold and how he acts. That's kind of the way I felt. So according to my wife. All right, so what happens with this lizard is as the temperature goes down, the chemical reactions in this body start to slow down, as what happens with all chemical reactions. You cool them down, things start to slow down. So what happens is that the animal can become lethargic, slow down in its movement. Same thing happens with things like snakes that we can see that typically don't move around that much in the winter. But kinetics is simply the studies of the factors that control the rates of chemical reaction. And temperature is certainly one of those things that we're going to look at. So how fast a chemical reaction proceeds is called the reaction rate. Speed, if you want to think of it as speed. What a rate is a measure of is how much of a product a reaction produces, or how much of a reactant is being consumed. One's related to the other. If you look at the disappearance of a product, you could look at it that way. How fast is a disappearance of a reactant? The things that are on one side. So I've got A plus B yields C in a very simple reaction. I can study this by looking at how fast A disappears or how fast B disappears. In a similar fashion, I can study this and how fast C starts to appear. And the key thing, if I know what the stoichiometry is, what the little a would be, the little b, the little c, the moles of each one of the reactants to the products and what those ratios are, if I can study any one of those, I know the relationship to the other. So I don't have to know what's happening to A, B, and C simultaneously. When I study kinetics, all I have to know is what happens to one of them. So any one of them that I can measure will tell me everything that I need to know. All right, so the ability to control how fast a reaction goes is critically important. One of the We talked about lab safety at the start of the semester. One of the big things that we have to think about or causes the most types of accidents are reactions that are runaway reactions. They produce too much heat. It causes something to expand. It causes an explosion. It causes a solvent to ignite. It causes a fire. So of reactions that are tremendously ectothermic, we typically run them at low temperatures to control how fast they go, how much heat that's given off in a system. We have to understand what's the factors that influence this. So we define the rate. If you think about any way that you define rate, like the speed on your speedometer, and when you think about it in your speedometer in your car, what are the units of your speedometer?
Miles per hour.
Okay, so it's miles, mph, it's miles over hours. All right, so miles represent distance, and hours represent a passage of time. So it's the change in distance over the change in time tells me something about my speed, how much has changed. Same thing happens with a chemical reaction. Instead of looking at distance, now we're interested in moles, okay? So it's the same type of a concept, and if we know what miles per hour are, I could convert it to any other unit. I could get it in meters per second if I wanted to, just by knowing some dimensional analysis terms. How many feet are in a mile? How many meters are in a foot? How many seconds are in a minute? How many minutes in an hour? I could convert that into anything else that I wanted to in terms of units. In terms of a chemical reaction, the way that I look at these terms is I look at how concentration changes. All right, so I'm looking at, is there an increase or a decrease? So if a reactant, I'm looking at how fast it's going down, decreasing. If I'm looking at the product, I'm looking at how fast it's going up, increasing as a function of time. For reactants, the way that I represent this is with a negative sign put in front of the definition. Right, so I don't know why it, hope it didn't do that in your notes. I don't know why it spaced that out like that. It's supposed to be the word concentration. The rate is the change in the concentration divided by the change in time. So if it's a product, it's just the change in. Okay, so how do we find the change in? So if we found the change in temperature, what did we do in our equation? Okay, same thing here. It's going to be the final concentration less the initial concentration. Right? So change in is going to be the final concentration of the product less the initial concentration of the product divided by the passage of time. Now the only difference in products and reactants is that if it's a reactant we're looking at it as disappearance, so we add the negative sign to it. So for reactant, it's a change in the concentration of the reactant divided by the time, we take the negative of that. So the bottom example tells us how we could define the rate for this reaction. And the reaction is hydrogen gas reacts with molecular iodine to produce HIs, and it produces 2 HIs. So if I look at the rate and define the rate of this and with respect to the hydrogen is a reactant, and the fact that it's a reactant means I'm going to have a negative. So it would be the change in the hydrogen concentration divided by the change in time. Now we're going to use this a lot, so let me make sure that you clearly understand what that means. Whenever something is inside of these square brackets, this represents concentration in molarity or molar. So square brackets represent molar concentration. Okay? So anything inside of square brackets means molar concentration associated with it. So what I need to do is look at what's the change in concentration of the hydrogen ion, or of the hydrogen H2 divided by the change in time. So the way that I would find change in concentration is it's the final T2 concentration less the initial concentration, T1, divided by the passage of time. What's the difference in T1 or T2 less T1. Now, in some cases, we may start the clock at 0, and T1 would be 0. There are going to be other times that if we think of starting something at 0 in terms of time and measuring, I may be interested in what's happening at 10 to 20 seconds. So it's not always going to start at 0. Okay, and we'll see this as because rates change as concentration change with some types of reactions. And to understand what's going on, you don't always start at the 0 passage of time for T1. Okay, so here's an example of this graphically. These are a couple of, this is that same chemical reaction we just talked about. H2 plus I2 yields 2 HIs. And what we have is initial concentration of H2. All right, and it's starting off at 1 molar. And if I look at the passage of the time, this is time in 20 seconds, so it's going from 0 to 120 seconds in time. And I've got the thing that's in blue represents my H2 gas, and its concentration is diminishing as a function of time. So it starts at 1 molar, and at 40 seconds, it's down to less than 0.5, right? So it's at this point. And at 80 seconds, it's about at 0.2. If I keep going down, it diminishes accordingly. All right. Now, if I look at what's happening with the other reactant or the other product in the system, okay, the product that's in this is the HI. It's starting off, there's none of it initially, but as soon as the reaction starts, it starts to form it. Its concentration is going up. And what I'll see on this is it goes up higher if I look at this change, okay, versus the other change, it's much larger. And the Y is because of the 2 stoichiometry. It's producing 2 moles of the product for every 1 mole of the reactant that's consumed. Okay, so it's increasing, and I can look at how much it's increased, and I can study this and predict it. If I know something about these relationships, if I know at any point what's happening to the H2, I can predict what's happening to the HI. So I could, if I know where I'm at here on the H2, I can tell you exactly what's happening here on the HI in the system. The two things are related to one another. Now, at any point, I could calculate the slope with this. So let me erase my writing a little bit. Okay, so I could calculate at any point what's the slope of this line, and that would tell me the rate. Okay, so if I think about the slope is the change in y over the change in x. Okay, we calculate slope of lines. And if I look at this one, y is the concentration, so it's the change in concentration over the change in time. But that was our definition of what the rate is. So the slope of this at any point represents the rate of this chemical reaction. So if you take something that's a straight line, the slope stays the same. But in these examples, the slope changes as a function of time. It's not constant slope. It's changing depending on how long the reaction's been going. And at some point in time, these two things will level off, and then it may become steady state, not changing anymore. The way that we find the slope of the line is we could take a tangent curve, right? So draw a line that's exactly parallel with any given point. And if I looked at how the tangent curve would change at different positions, I could see how that, here it's here, I went down towards the end here, it's different at different positions. Every one of those lines, green, blue, red, have a different slope associated. And that represents how the rate's changing on that particular reaction. So we could take and do if we're giving something graphical, if I wanted to know change in y over change in x, remember, turn your phones off so you don't get in trouble. All right. Change in y, concentration, I could take this point versus this point and measure the slopes. I know this point to this point, it's about 0.56. The passage of time from here to here is about 40 seconds. I can calculate what the slope is for that. by taking the change in concentration divided by the passage of times, and it's going to give me an answer. It's a little bit greater than 1, so 1 something. Molarity per second. So rate has units of molarity per second associated with it. Now that's looking at data graphically. We don't always see data graphically in systems. Sometimes we'll look at it just with the numbers. Okay, so gotta get a drink. What happens as time goes on, the typical thing that we see is the reaction rate slows down. So the slowing down is the flattening out. Okay, you run out of reactants is what it comes down to. Okay, so as most reactions go on, you can make a reaction go to 90% of the product, maybe in a minute, and in another 10 minutes it'll go to 95%, and then in another hour it'll go to 97%. But to try to get it to 100% takes days and days and days. So a lot of times we do reactions and look at percent yield. Our low yields are actually the influence of slow kinetics, and we just didn't let it go long enough. Okay, so one way that we can speed reactions up, going back to the lizard, if you want to make a lizard run fast, put him in a hot pan. Okay, and I'm not saying be cruel to lizards, but in the heat of the summer, have you ever tried to catch a lizard in the heat of the summer? Have any of you been camping and tried to chase a lizard? Some of you have, okay, you're not going to admit it. They can hook, okay, they can move. All right, so you move and you try to grab them and they're not where you just put your hand. So, but in the winter, that's the time you want to try to catch a lizard. Same thing, chemical reactions, they're a function of temperature. Okay, so the reason they slow down is because the reactants are not as common. For a reaction where you have A plus B to form C, the atoms or molecules of A and B have to physically run into each other and have to come in physical contact in the solution, the solid, or the gas, whatever phase they're in, before they can combine to form the product C. If these things are not very common to one another in terms of concentration, only randomly are they slowly going to start to interact with one another. So higher concentrations are in favor for reactions to go fast. When concentrations decrease, the reaction slows down. Now at some point the reaction stops because there's either run out of reactant or because the system has reached equilibrium. Equilibrium means that the system is decaying. C is reverting back into B and A at the same rate at which it's making new product C. So there's no effective change in concentration. The way that we would see an equilibrium on a graph is when the curves went to a slope of 0. So if you let this graph go out long enough, and if it ever flattened out, okay, became flat down here. So in either case, the slope is 0. That represents a point of equilibrium. There's no change in concentration. Okay. So average rate. An average rate is the change, okay, at any particular point in time, whatever that time is. And what we commonly do is we'll do a linear approximation for a curve like we showed on the other one. We'll take draw a tangent line, and what is the slope of that tangent line that we drew. And the larger the time interval becomes, the more the rate deviates from the instantaneous. Okay, what does that mean? Well, if I look at a very large window and I say, okay, tell me, I want to measure 2 points, and I'm going to choose these 2 points to tell me the slope. And I'm going to look at what are their concentrations and what's in the passage in time. And that can tell me something about a slope. All right? So, and that slope tells me something about the rate. But if I look at another pair of points, so if I looked at this point and this point that are far apart, what I see is that these slopes don't match each other. Okay? So the farther my points are apart, the further this is a deviation from what the true rate is. So is this a good measurement of what the true rate is at any point? So to get good data, we have to make measurements very quickly. So a lot of times when you do chemical kinetics, if you have a fast reaction, you have to have a system that's capable of measuring the concentration every second. 10 times a second. 1,000 times a second. In high-speed reactions, there's a special form of a chemistry that measures reactions using a laser every femtosecond. The femto is 10 to the minus 15. Okay, so if you have something that's a very high-speed reaction, you have to be able to monitor it that quickly. When you think about this, it collects a certain number of data points per second. So if you win a second, there are 10 to the 15th data points that are collected. You fill up a flash drive in a second's worth of data in a system like that. So there are times where rates are that fast. A lot of the biological processes in the body we've learned just in the last years. We used to think that A went to B, and some enzyme allowed that to happen. Now we're starting to learn that A went to intermediate C, and intermediate C converts to intermediate D, and intermediate D went to intermediate E, and then finally E converts to A. All right? All of these steps happen so fast, we never even can detect any of these intermediates present. And it's only when we started to study actual enzymes themselves, and we started to look at the structure, three-dimensional structure of enzymes, that we've started to realize that the biology of life, the chemistry of life, is a lot more complex than we thought it was. So when you look at something that describes the glycolysis pathway in a biology book or a biochemistry book from the 1960s, it doesn't look anything what it looks like today. Okay? It's not because the products they still knew glucose was going in and they knew what was coming out of it. It's the intermediate steps that are happening so quickly that we didn't even know that they were there. All right. So if we look, this is the same data that we had, and this is more like how we're going to see our data. So this is the graph that we looked at, the disappearance of H2 and the formation of HI. Those same time intervals every 10 seconds, and it's still going from starting at 1 molar of the reactant and going down to 100 seconds of time. So here's our time, here's the initial concentration of the reactant. We can look at those in terms of the rate. If I look at the change in concentration of H2 and the passage of time, and if I look at every 10-second interval. Okay, so the first 10 seconds, if I look at the change in concentration of H2, it measures 0.819. So the difference, the final less the initial, this comes up to a negative 0.181. Now look at the time that happened in 10 seconds. I can divide the two and I can get the rate in that first 10 seconds. And then I can look at between 10 and 20 seconds. And I can measure the concentration at 20 seconds. I can get the concentration or the change in concentrations, again, 10 seconds. I find the rate. And I'll see that I can calculate the rate at all these different points. And it's only down at the end when they start to slow down and get close to one another. There's big differences initially in 10-second intervals. It's changing very rapidly as the reactant's being consumed. And I can relate those to the product in the systems. So the instantaneous rate is different from the average. It is the rate at any one particular point in time. So it's the slope on the curve. The instantaneous rate would be like looking at your speedometer And the moment you look at it, it's how fast you're going. Okay? Where the average rate would be setting the trip on your speedometer, the trip function, and how long did it take you to go to Oklahoma City. And let's say you drive to Oklahoma City and you get stuck on the traffic on I-35, because it sucks right now if you drive up I-35. Every day you're doing something. And you get stuck on the traffic up somewhere in there, and maybe you only average 50 miles per hour. Well, if you drive 50 miles per hour on the interstate, semi's going to run right over you, okay? Because everybody averages, I set the cruise on like 78, and I'm setting still plus some people. I mean, they're flying. You're going to go fast, you're going to go through Medill, and you're going to have to come to the stoplights and stop. I mean, you're all types of instantaneous rates or speeds are changing. Rates, if we think of it in chemical reaction, you're going fast, you're going slow. Instantaneous is that one moment in time. It's the speedometer at the moment you look at it. Hopefully it's not above the posted speed limit. Don't drive north on 78 above 60 miles an hour, I'll warn you. Since they open that up into a 4-lane, you'll meet a highway patrolman that will explain the limits to you. So that's where I live now. So they are working that little 5 miles north of town. Okay, so instantaneous rate can be determined by taking the tangent. As long as we've got a good curve that describes this, if we go to any point and find the tangent, those of you that had calculus, you'll know that the tangent can be found by taking the first derivative of the curve. Right? We're not going to do calculus in here, but just an application of why did I learn this stuff. Okay, so as time goes on, what happens is reaction rates will slow down because concentrations decrease. We've said that. And at some point, the reaction either stops or the system reaches equilibrium. That sounds deja vu-ish. Okay. So now when we look at the coefficients of the balanced reaction, so in this one, it's 1, 1, and 2. What that does is it tells us some information about the number of molecules of the substance related to the factor of the other substances in the reaction. Okay, so for example, if we look at this reaction, I know for every mole of H2 that's consumed or used, there also has to be a mole of I2 that's consumed, and there's going to be 2 moles of HI that are going to be formed as products. Okay, and those are defined by the stoichiometry. You can't deviate from that. So because everything that has a different balanced stoichiometry, the numbers are different, that means that its rate of change is going to be different. So the way that we represent this, or we show the rate of change for each substance, is we multiply by 1 over the inverse of the coefficient, where the coefficient's the coefficient of the balanced reaction, 1, 1, and 2 in this case. So if I look at a particular reaction, if it were the reaction, let's see if I can extend the page out a little bit. All right, so if I had the reaction little a plus a, little b plus b yields little c plus c, and little d of d. A plus b yields c plus d as products, and the littles a, b, c, and d represent the coefficients. Okay, the rate that I would write for a, okay, with respect to A, would be the inverse of the coefficient, the times the change in concentration of A over the change of time. And the fact that it's a reactant that's on the left-hand side, so it's on the left side of the equation, means it's going to have a negative with respect to it. B is going to be the same way. So if I could monitor B, the rate would be the negative of the inverse of B times the change in concentration of B divided by the change in time. Now, if I look at the other side of it, the things that are being formed, they're represented by a positive sign. So, but the same thing, the inverse of C times the change in concentration of C divided by passage of time, and similar for D, it's equal to a positive, the inverse of D times the change in concentration of D divided by the passage of time. And these things are all related. Okay, they're all related, being equal to the rate. So if I can monitor any one of, in this case, 4 things, I know the relationship to all of the others. Okay, so we could plug the numbers in if we wanted to find the instantaneous rates, and we found the slopes to our equation. We get a tangent line, and we find the slope. Okay, if I found it at 50 seconds, so here's my 50-second mark that I'm finding the slope for, and I'll go to the H2, so here's my H2 one. I got the slope here, and I find its rate is a negative 0.28 divided by 40 seconds. The rate for it is 0.007 molar per second. And now if I look at how that would compare at the same time for the product that's being formed, if I look at the HI that's being formed at this same passage of time, its rate would be its change in concentration divided by the 40-second time period. And because of the rate on this one, it'd be divided by 2 because the 2 stoichiometry. I find that it's also 0.0070. The rates are the same. It doesn't matter if I'm looking at the product or the reactant. Okay? So it gives me a way that I can tackle different systems and understand how they work. All right, let's see if we can look at some examples. So I want to write the rate expressions for this series of reactants. So rate equals what? Clicker question coming soon to you. Okay. So first thing I'm going to do is start looking at the reactants. Okay, starting with the left. So it would be a negative. All right, so this is a 1, a 2, a 1, and a 2. All right, so it would be 1 over 1, which is just 1, over the change in concentration of methane over the change in time. All right. Then if I look at it for the O2, it would be a negative 1/2 of the change in concentration of O2 over the change in time. And if I will look at for the products now, it's a positive 1 over 1 change in concentration of CO2 divided by change in time. And then finally, the last product in this one, a positive 1/2 times the change in H2O over a function of time. So we can look at it in terms of products or reactants. The only difference is that we have to be sure for all of the reactants to apply the negative to it. Products are always positive. All right. So I get to write that down. There you go. I want to know which one is the rate of the reaction with respect to the reactant sulfur dioxide. Staying on the far left. That's a couple. More. Need one more vote. I counted 16 of us. Last chance. Vote again if you're not sure. Yours didn't go. Okay. All right. So predominant answers are A and C. Gosh, if it's B, it's going to be terribly disappointing. It's not, it's A. Okay, we'll review this and start up on material on Wednesday. All right, we got a lab this week. Sometime this afternoon, I'll get the lab posted we're doing this week.